working. So yeah, so enthalpy changes. So there'll be a little bit of a recap just to start us off on Friday, just to sort of remind ourselves what enthalpy is. A little quick recap of Hess's law, but only short. And then we'll look at bond energetics. Then we will move on to kinetics. So enthalpy changes. Enthalpy, we sort of have to know about quite a lot of different things. So thermodynamics, enthalpy changes, standard enthalpy values, and lots of these were what we covered on Friday. So the basics of enthalpy, you should be able to balance equations and be able to do basic arithmetic to be happy with enthalpy, which I suspect I have no issues with either of them. So thermodynamics, this is actually really quite important to remember. It always comes up all the time, but energy can either be created or destroyed, but it becomes converted from one form to another. And this is the whole basis of enthalpy. So energy changes. So all chemical reactions are accompanied by some form of energy change. So like we were talking about on Friday, somewhat exothermic, so energy is given out, i.e. coal burning, but others can go unnoticed. And then we also have those endothermic reactions, which aren't as common, things like photosynthesis, and that's where energy is absorbed. So some main examples: exothermic, combustion of fuels, respiration. Main examples for endothermic: photosynthesis, thermal decomposition of something like calcium carbonate. And so that's our difference of energy is being either given out or taken in. So quick recap of enthalpy, what enthalpy is. So enthalpy is a measure of the heat of a substance at a constant pressure, so 100 kilopascals. You cannot measure the actual enthalpy of a substance. You can measure an enthalpy change. So that's really important. So enthalpy change is delta H, and that is our change of enthalpy. So we have our enthalpy of our products, take away enthalpy of our reactions. So we can't work out the enthalpy of a reaction, but we measure an enthalpy change. How much has it changed from what it was as a reactant? How much enthalpy was in the reactants? How much enthalpy is in the products? And like we had a look at on Friday, we get these really nice enthalpy diagrams, very, very similar. So using these, we can tell if a reaction is exothermic or endothermic, and we can calculate the delta H, the enthalpy change. So here we can clearly see that our enthalpy of our reactants is higher than our enthalpy of our products. That means, well, we've got our activation energy here showing that we need that increase of energy for that chemical reaction to take place. And then down here, we've got our delta H, our enthalpy change. So this is our enthalpy change that happens. That means we're going to have a negative enthalpy change because we've decreased from our enthalpy of our reactants to our enthalpy of our products, which means that heat is given out, energy is given out to the surroundings. So we have an exothermic reaction. In comparison, we've got the opposite with an endothermic reaction. We have a lower enthalpy of reactants than enthalpy of products. This is our activation energy. Therefore, our enthalpy change will be a positive because our reactants has a lower enthalpy than our products, which means it's an endothermic reaction, meaning heat is going to be absorbed. So these standard enthalpy changes that we talked about again, 100 kilopascals, also known as 1 atmosphere. So this is our standard enthalpy change. These are the conditions that the substance should be under for it to be said it's a standard state. So it's really important to remember this. So 100 kilopascals pressure, a stated temperature, it's usually 298 Kelvin, 25 degrees. As a guide, basically, we think of how a substance would be under normal lab conditions. We assign this a correct subscript, gas, liquid, or solid to indicate which state it's in. Any solutions of a concentration of 1 mole per decimeter cubed. And to tell if standard conditions are used, we modify the symbol for delta H. So this is our standard enthalpy change because we're saying it's in standard conditions. Standard, we've got our standard with our delta H, and we're actually saying what our temperature is. We're stating our temperature, and it's 298 Kelvin in this situation. So that's really important. Basically, we're thinking, what would the lab be? Generally, most labs are going to be around 298 Kelvin, the temperature of them. So enthalpy change of formation. So the enthalpy change when 1 mole of a compound is formed from its elements. So this is what we started to talk about and linking it with Hess's law. So standard enthalpy change of formation, that's our delta HF, the enthalpy change when 1 mole of a compound is formed in its standard state from its elements in their standard state. So it's all about that standard state again. We want to keep all of those standard states controlled. So we can show it as delta FH or delta HF is our symbol. They're usually exothermic, but sometimes they're not. Okay, so an example. Graphite plus oxygen, we get carbon dioxide. We could have hydrogen plus oxygen to get water, or graphite plus oxygen gives us hydrogen. Oh, plus hydrogen gives us C2H5OH. So only one mole of a product on the right-hand side of the equation. So it's 1 mole to 1 mole. Okay, so it's 1 mole of a compound being formed from its elements. So we should only ever have 1 mole on the right-hand side. If we've got more than 1 mole, then we will need to change things. So this is enthalpy change of formation is really important when we're only dealing with 1 mole. So elements in their standard states have 0 enthalpy of formation because they're in the standard states. They have not formed into a molecule or a compound. So we're saying it has 0 enthalpy of formation. Carbon is usually taken as the graphite allotrope, and that's just what we normally use there in that situation. We're just going to look at combustion now. So that's formation. So that's how we form a compound. And we would work out from there. And we will have a data set, and you'll be given data sets of actually working out how much enthalpy is coming from one to the other, because we say the elements have a 0 enthalpy. And so then we work out what that enthalpy change of formation is, and we'll get given that. And if you're asked questions about this in the exam, you'll be given a data table with this information in to then use for something like Hess's law, for example. Enthalpy change of combustion. We didn't actually talk about this on Friday. So the enthalpy change when 1 mole of the substance undergoes complete combustion. So that's delta CH or delta HC, doesn't matter which way around it is. And again, then we can have standard enthalpy change of combustion. Exactly the same as enthalpy change of combustion, but this is when the enthalpy change when 1 mole of substance undergoes complete combustion under standard conditions. All reactants and products are in those standard states. Therefore, we're talking about that controlled pressure, that controlled temperature. These are always exothermic. It's a combustion reaction. So we've got examples of graphite and oxygen making carbon dioxide. Again, the same as enthalpy change of formation. It is always only 1 mole of what you are burning on the left-hand side of the equation. So whatever is happening over here on the left-hand side, it is always just 1 mole. And to aid balancing the equation, you need to remember you get 1 carbon dioxide molecule for every carbon atom. So for 1 carbon atom, you get 1 carbon dioxide molecule in the original, and 1 water molecule for every 2 hydrogen atoms. Once you've done this, you can then go back and balance the oxygen. So that's how we end up with half O2 and just O2 here, because we need to then go backwards and balance this for 1 mole. And that's really important that we're balancing this for 1 mole. We use half O2 because obviously oxygen always comes in a pair. We obviously only need 1 oxygen in this situation, but we can't just write O because oxygen always comes in that pair as O2. So we write half O2 because realistically, we wouldn't actually just make 1 mole of water. We'd probably be making at least 2 moles, if not more. But for this, how we write these equations and for our enthalpy change of combustion, it always needs to just be 1 mole. So we then want to work backwards and balance in the opposite way. So why is this not moving on? We can also have enthalpy of neutralization. Funnily enough, the definition is almost the same as the other two. This is our enthalpy change when 1 mole of water is formed from its ions in a dilute solution. So again, we can have delta neut H or delta H neut. This again is an exothermic reaction. So our equation would be H plus in an aqueous solution plus OH minus in an aqueous solution goes to H2O in a liquid. A value of minus 57 kilojoules per mole is obtained when strong acids react with strong alkalis. Okay, so that's really important to remember. And then we can start to talk about bond dissociation. And so this is when we're talking about when we're breaking our bonds. So this is our bond energetics. So this is the energy required to break 1 mole of gaseous bonds to form gaseous atoms. And this is actually really important now that we're actually paying attention to what states that we're talking about. So back here, actually, we've had aqueous and things in aqueous state and liquid state. We've got mixtures of gases and liquids, gases, liquids. But here, bond dissociation, it's gaseous to gaseous atoms, okay? So this is to break a mole of gaseous bonds to form gaseous atoms. We are breaking a bond, we are breaking a compound down to its atomic form. Therefore, it will be an endothermic reaction. The energy must be put in to break those chemical bonds. So we go from Cl2, which is a chlorine. Chlorine is a form, as it's forming gas, is a compound. It's always found together. To break them, it would become 2Cl in a gaseous form. Okay, and that's because we have 2 separate chlorine gas atoms. Another example is our OH, gaseous. We'll go to O plus H. So our strength of our bonds also depends on the environment. So what we do in these situations is you'll be given bond formation tables again, similarly to when we talked about Hess's law. And these are mean values quoted. If the environment's different, then we're talking about things like temperature, pH, the strength of the bonds can differ. So we talk about the mean values. What's the average amount of energy that is needed to create these, to break these bonds? As we can assume from this, if we're breaking a bond dissociation is an endothermic reaction. Therefore, making bonds is exothermic. It's just the opposite of each other. So for diatomic gases, so things like chlorine, bond enthalpy is 2 times the enthalpy of the atomization. And a smaller bond enthalpy means we have a weaker bond, which means it's easier to break. So that gives us some sort of clue, actually, if we're then starting to look at bond enthalpies and if we're looking at a molecule, which molecule is it going to be easiest to break? Which one will break first at this temperature? Well, actually, the smaller the bond enthalpy, that means that bond's weaker. It's going to be easy to break. It requires less energy to break it. And here's some example of those values. So you get lots of these coming up. So for example, so the average again, because actual depends on the environment, and it actually can depend on where actually the bond is in the molecule because of different parts of shielding, and if it's in the middle of the molecule, other things might need to break first before we can get to it. So these are just mean values. As you can see, we have a huge range. Our weakest one on here is, I'm just going to double check I'm going to say the right one, oxygen and oxygen, at 146 kilojoules per mole. Hydrogen bonds, like we've talked about before, hydrogen bonds being fairly strong. So hydrogen to hydrogen, we've got 436, carbon and hydrogen 413, hydrogen and fluorine 562, hydrogen and chlorine 431, hydrogen and bromine 366, hydrogen nitrogen 488, hydrogen oxygen 463, hydrogen sulfur, hydrogen silicone. So we've got those strengths. What's nice is when we have carbon-carbon, we can look at single bond, double bond, triple bond, and how much stronger that is to break every time. Obviously, it seems quite logical. We've got a triple bond between a carbon and carbon. It's going to take more energy to break that down. Our highest one to try and break down on here would be nitrogen triple bond. So that's 944. So that would be one of our strongest bonds that we need to break. But yeah. So that's a good idea. You will be given these. You're not expected to memorize these or learn these, but it's a good idea to sort of know roughly what sort of values you're sort of expecting to see. So yeah, let's look back at Hess's law again from Friday. So Hess's law states that the enthalpy change is independent of the path taken. So the idea is if we go from A to B, the enthalpy at A to B, which might equal 20, if we actually went from A to X, X to Y, Y to B, if we add all three of those enthalpy changes up, we would get the same value as the enthalpy change from A to B. And that is the idea behind that. So the enthalpy change going from A to B can be found by adding the values of the enthalpy changes from reactions A to X, X to Y, Y to B. So A to X, so this is used when we can't work out the enthalpy change from in a practical element, so we can't actually experimentally calculate the enthalpy change. So instead, using those bond formation information and formation and enthalpy change of formation, we can actually say, well, this is A, X is going to be those the atoms that constitute it. So actually, what's needed to break, what are those bond changes where those bond dissociation from get A to X, so what is that bond enthalpy change going to be there? X to Y, how are we going to get from these individual atoms to these individual atoms, and then Y to B, what are the bond changes happening here? If you go in the opposite direction of arrow, you subtract the value of the enthalpy change. So for example, if we had delta HR and we want to work out delta H2, you would do minus delta HR minus delta H1, because we're going in this direction. Actually, let me put my pen on. There we go. So if we want to work out what delta H2 is, if we're going in the opposite way, we're going against that, we're going to subtract that value because we're going against it. And then we would go, I want a different pen color actually, so we can see what's different. So yeah, we want to work out what delta H2 is. So we're going to go this way, we're going against the arrow. So we're going to subtract whatever delta H1 is and go this way. So we're following the arrow again. So that's going to be a positive. We're going to add that. But again, we're going against this one. So we'll take that one away. So it would be negative delta H1 plus delta HR negative delta H3. And so we're subtracting delta H1 and delta H3 because the root involves going in the opposite direction to their definition. That's really important to remember, and you can get asked to come out with different ones. In a similar way, you could get asked, let's get rid of them, to find delta H3. Oops. Delta H3, so you might go this way. So we'd subtract that one, go this way, subtract that one. Oops. Go this way, we would add that one. So yeah, we can go in a few different ways. Okay, so Hess's law enables us to calculate enthalpy changes from other data, such as changes which can't be measured directly. So lattice enthalpy, we can't measure them directly. And enthalpy change of reaction from bond enthalpy, enthalpy change of reaction, and enthalpy changes of formation. Okay, so enthalpy of reaction from bond enthalpies, that's what we're going to have a look at now. So what we're going to do is we're going to imagine that during a reaction, all of our bonds of reacting species are broken, and then the individual atoms join up again in the form of the products. So the overall energy change will depend on the difference between the energy required to break the bonds and those bonds are released. So that's basically what we've just been talking about with Hess's law there. So basically we're going from here to here, basically works out what is the energy change to break them bonds. So what is the endothermic energy to break those bonds? What is the exothermic energy to make them bonds? And how do we get there? So energy released making bonds. Energy released making bonds is greater than our energy used to break bonds, exothermic. Vice versa, we've got endothermic. So step one, what you would do is energy is put in to break bonds to form separate gaseous atoms. Then the gaseous atoms then combine to form bonds and energy is released. Its value will be equal and opposite to that of the breaking bonds. So basically we apply Hess's law. So delta HR equals step 1 plus step 2. We can look at this in a different way. Same thing. So energy is put in to break bonds to form separate gaseous atoms. And gaseous atoms then combine to form bonds and energy is released. Its value will be equal and opposite to that of the breaking bonds. So this time we're doing delta HR equals step 1 minus step 2. So we've got our products at the bottom, atoms at the top. So delta HR enthalpy change is enthalpy bond enthalpies of our reactants minus our sum bond enthalpies of our products. Very similar if you think to just working out an enthalpy change if we have the enthalpy data. But this time we're looking at bond enthalpies rather than just enthalpy. Because in step 2 the route involves going in the opposite direction, it's then defined change of bond enthalpy, its value is then subtracted. So we then subtract that one because we're going in the opposite direction. So what you can get asked is something like this. You can get given this image and you can get asked to calculate the enthalpy change for the hydrogenation of ethene. So what you would need to do is work out, we don't know basically what this is. We don't know what delta H, why is my pen not working? We don't know what delta H1 is, so we need to work out what delta H2 is. So we're going to look at delta H2. Okay, so we need to see how much energy is required to break one double bonded carbon. That's 611. We've only got one, so it's 611. And we've got 1, 2, 3, 4 carbon hydrogen bonds at 413. Multiply that 4, we've got 1,652 kilojoules. And then finally, we've also got our hydrogen bond, so 436. Add all them together, so our delta H2 value is 2699 kilojoules. Then we're going to work out delta H3, if my mouse would work. So delta H3, exactly the same as before. We've got one carbon to carbon bond, which is 346, and then we've got 1, 2, 3, 4, 5, 6 carbon hydrogen bonds at 413. Multiply that by 6. So what you would do, again, these values would be given to you in the exam. You just need to pick out the right amount of them that you see in the images. And so the total energy to break the bonds of these products would be 2824. So to work this out, to work out delta H1, we do delta H2 minus delta H3. So 2,699 take away 2,824 would give us minus 125 kilojoules. We've got a negative enthalpy change, which means we've got an exothermic reaction. We can do exactly the same thing, but instead of using bond enthalpies, we can use enthalpies of formation. So bond enthalpies, we're going in this way. So bond enthalpies, we're basically saying how much energy is required to break all these bonds, how much energy is required to break all these bonds. We can do energy of formation, where it's how much energy is required to form these bonds and form these bonds. Enthalpy of formation is usually an exothermic process, making bonds. So this time we're going to have our enthalpy of our products minus our enthalpy of reactants. So we're still doing enthalpy of reactant products minus enthalpy of reactions. So an example. So you might get asked to calculate the standard enthalpy change for the following reaction, given that the standard enthalpies of formation of water, nitrogen dioxide and nitric acid are minus 286, plus 33 and minus 703 kilojoules per mole, respectively. The value for oxygen is 0 as it is an element. So let's have a look at what our enthalpy of water would be. Well, our enthalpy for water, we've got H2O. So we're doing enthalpy of formation. So we're going to look at how much energy is required to form these. So we've got formation of water, and we've got 2 lots of water here. So that's minus 286. So that would be 2 lots of minus 286. So minus 286, I'm just going to twice minus 286, minus 572. So our enthalpy of formation for water would be minus 572. We've got nitric acid and nitrogen dioxide. Sorry, here nitrogen dioxide. We've got 4 lots of it. Nitrogen dioxide is plus 33. We've got 4 lots of 33, which would give us, no, that would not give us 37. 4 lots of 33 give us 132. Oxygen is 0. So let's add them together. We've got minus 572 plus 132, which would give us in total minus 440. Let's have a look what our product is. Well, our product is nitric acid, minus 173 kilojoules per mole. We've got 4 lots of that, so we're going to do minus 173 multiplied by 4, which will give us minus 692. So bond enthalpy of products minus that of our reactants. So we're going to do minus 692, take away 440, which would give us 252. So 692, which gives us 252, so minus 252. So again, if we have it here, we've got products minus this plus this plus this equals that. Enthalpy of a reaction from enthalpies of combustion. We can also work this out using enthalpies of combustion. So if you burned all our products, what should happen is you should get the same amount of oxidation products, such as carbon dioxide and water, as if you burn the reactions. So this is an exothermic process. So this time we're going to do reactants minus products this time. So different, we're going to do reactants minus products. So here's our question. Calculate the standard enthalpy of formation of methane. The standard enthalpies of combustion of carbon, hydrogen and methane are minus 394, minus 286 and minus 890. So enthalpy is combustion of carbon. We've got 1 lot of carbon here. That is, what did we say it was? Minus 394. So let's pop that on. So we've got minus 394 plus hydrogen. We've got 2 lots of minus 286. So 2 lots of minus 286 is minus 572. And then our products, we're going to take those 2 numbers away from our product number, which is 890, or minus 890, sorry. So minus 394 plus minus 572, take away, which gives us 966. 966, take away 890 will give us minus 76 kilojoules per mole. So another exothermic reaction using Hess's law. I'll miss that for now. Okay, so no, we will do this. Okay, so measuring enthalpy changes. So one way we can measure enthalpy changes is using something called calorimetry. So what this does is this involves the practical demonstration of enthalpy changes, and it usually involves heating or cooling known amounts of water. So if we heat water up, it's exothermic, and if we cool water down, it is endothermic. So what we have to do is the energy required to change the temperature of a substance can be calculated using this. You need to know this equation. So Q equals M times C times delta T. Q being your heat of energy in kilojoules, M being mass in kilograms, C specific heat capacity. Water is 4.18, and then delta T is your change in temperature, which we should be measuring in kelvins. So here is an example. So on complete combustion of 0.18 grams of hexane, raised to a temperature of 100 grams of water from 22 degrees Celsius to 47 degrees Celsius, calculate its enthalpy of combustion. Okay, so our enthalpy of combustion is Q. So we're going to do M. So we're going to get, we want to work out our heat absorbed by the water Q. So we're going to do 0.1. 0.1 comes from obviously our water, because our water mass is 100 grams, 0.1 kilograms. We're going to times that by 4.18. 4.18 is our specific heat capacity of water. And we're going to also times it by 25, which is our change in temperature. Change in temperature is 25 degrees Celsius. So our heat absorbed by the water, Q, equals 10.45 kilojoules. Okay, so let's look at the moles of hexane burnt. Well, our mass is 0.18. Our relative molecular mass is 86. So 0.18 divided by 86 would give us 0.00209. Finally, to work out our enthalpy change, we just need to do our heat energy, which is Q, divided by moles. So we've got 10.45 divided by our moles of hexane, which is 0.00209, which should give us 5,000 kilojoules per mole as our enthalpy change. We can also measure enthalpy changes graphically. So the temperature is taken every half minute before mixing the reactants. So that will give us our temperature at the beginning. Our reactants are then mixed after 3 minutes. Further readings are then taken every half minute as the reaction mixture cools. And then what you would then do is extrapolate the lines as shown as the correct and calculate the value of delta T. So, for example, when 0.18 grams of hexane underwent complete combustion, it raised the temperature of 0.1 kg of water from 22 degrees Celsius to 47. So here is our temperature change here. Calculate its enthalpy of combustion. So heat absorbed by the water is MC delta T. So 0.1 multiplied by 4.18, which is our specific heat capacity, times by 25, because this is our 25-degree change here, because we've worked out that difference from there to there, extrapolated that line. Work out moles of hexane, same as before. And then we'll do our heat energy divided by moles. Example 2, here is another example of how to measure this. So we might have 25 cubic centimetres of 2.0 mole hydrochloric acid. And we add this to 25 cubic centimetres of 2 moles of sodium hydroxide in an insulated beaker. The initial temperature of both solutions was 20 degrees Celsius. The highest temperature reached by the solution was 33 degrees. Calculate the molar enthalpy of neutralization, and our specific heat capacity of water is 4.18. Okay, so you want to obviously work out your temperature change. So your temperature change, we can work out delta T straight away. Delta T, well, it was 20 to begin with. The highest it went was 33. So our delta T was 13 degrees Celsius. Then, why is it not working? Oh. Obviously, we like to try and do temperature in Kelvin. So if we could convert that to Kelvin, that would be fab. But our temperature change again, it is still 13 Kelvin, 13 degrees, 13 Kelvin. We want to work out our volume of resulting solution. So we've got 25 of one reactant with 25 of another reactant. So that should equal 50 cubic centimeters. So our volume in decimeters would be 0.05. We want our equivalent mass of water. So density is 1 gram per cubic centimeter. So we've got 50 grams there. Therefore, in kilograms, we've got 0.05. So we're going to do its mass, which is 0.05, multiplied by the specific heat capacity, 4.18, multiplied by the change in temperature, 13, which would give us 2.717 kilojoules. It's a positive number, so that'd be an endothermic reaction. So that's just our heat absorbed by water. Then we need to do the next part. So our moles of hydrochloric acid reacting is 2. So we're going to do 2 times by 25 divided by 1,000 would give us 0.05 moles. Same for sodium hydroxide. So moles of water produced would be 0.05. Enthalpy change per mole. We're going to do our heat energy divided by our moles of water, which then gives us 54.34 kilojoules per mole, which again is an endothermic reaction. So by this point, what you should be able to do is explain the differences between endothermic and exothermic reaction, understand the reasons for using standard enthalpy changes, recall the definitions of enthalpy of formation and combustion, write equations representing enthalpy of combustion and formation, recall and apply Hess's law, recall the definition of bond dissociation enthalpy, calculate standard enthalpy changes using bond enthalpy values, calculate standard enthalpy changes using enthalpies of formation and combustion, know simple calorimetry methods for measuring enthalpy changes, and then finally calculate enthalpy changes from calorimetry measurements. So what I'm going to go through now, so moving on to kinetics now, also known as rates of reaction. So we're going to look at the first part. So we're going to look at what you need to know, and we're definitely going to cover collision theory and methods for increasing rate of reaction. So maybe looking at surface area, temperature, catalysts, light, pressure, concentration. So before you start for this one, it's really important to know how the energy changes during a chemical reaction. So thinking about bond formation, bond dissociation, know the basic ideas of kinetic theory, and then know the importance of catalysts in industrial chemistry. So there's something to think back to at GCSE. You think, oh yeah, no, I can remember this. Catalyst, remembering, lowers the activation energy, increases the rate of a reaction. So chemical kinetics. Chemical kinetics is concerned with the dynamics of chemical reactions. So basically we're looking at the way reactions take place and the rate of that process. So how fast or how slow that reaction is taking place. We can look at it in two ways. We can either look at it qualitatively and quantitatively. At the rate of a reaction can be changed. So which way we can look at it in two different ways and how we can change the rate of reaction. So chemical kinetics play a really, really important part in industrial chemistry, because basically the time it takes for a reaction to take place and the energy required are of great economic importance. If it takes a really, really long time, it might not be economically viable. However, if we can make it really quick, but it costs a lot, again, it might not be economically viable. So we're looking for that sweet spot. We're looking for that balance between the two, where actually, yeah, this is taking a sensible amount of time, and actually this is costing a sensible amount of money. It's not costing too much, but it's not actually taking too long either. So the kinetic aspect of chemistry is often at odds with the thermodynamic side when we consider the best conditions for industrial production. So actually using thermodynamics, we can actually say, yeah, no, this would be the best. But they're often at odds with each other. So the concepts met in this topic can be applied throughout theoretical and practical aspects of chemistry. So we're going to look at collision theory to start off with. So collision theory. Particles have to collide with each other before a reaction can take place. So that's the first thing, okay? So if particles aren't touching, if particles aren't colliding, we cannot have a reaction. But just because a particle collides with another particle doesn't mean we're going to have a reaction. We have to reach, reactants must possess at least a minimum amount of energy, and that is our activation energy. And that's something that comes up a lot in biology as well. So for a reaction to take place, our particles must collide, and this must happen. Reactants must possess then at least a minimum amount of energy for that reaction to take place. So activation energy plus particles must approach each other in a certain relative way, and this is the steric effect. So it's not just hitting into each other, we also have the steric effect. So according to collision theory, to increase the rate of reaction, you need more frequent collisions. So we need collisions to happen more often, because we know not all collisions are going to lead to a reaction. So actually, the more collisions we're having, the more likely they are to lead to a reaction, because we're just having more of them, we're just increasing the chances. So to increase our amount of collisions, we can either increase particle speed or have more particles present. If we've got more there, they're more likely to collide with each other. It's like if we had a room with two people in, closed their eyes, wandered around, they would occasionally bump into each other, but not all the time. If we then put 50 people in that same room, they're going to be more likely to be collisions happening. Or we can speed the particles up. We also need to increase our rate of reaction, more successful collisions, because it's great having all these collisions, but if they're not leading to reaction, that isn't helpful. So to have more successful collisions, what we need to do is either give particles more energy, or we need to lower the activation energy. So that is two different ways we can get that. So increasing the rate of collisions. So following the methods may be used to increase the rate of a chemical reaction. So lots of these are things that you'll have heard of before. So increasing the surface area of solids, increasing the temperature, shining a light, adding a catalyst, increasing pressure of gases, increasing concentration of reactants. So let's look at surface area. This is probably the main one that you've heard about most. We talk about it loads in biology, increasing our surface area. So if we increase our surface area, we increase our chances of collisions, because basically we're exposing more particles to each other. So if we put in, for example, this block and wanted it to react, that is going to take longer to react than if we cut that block up into smaller chunks. Because if we cut them up into smaller chunks, we've got more particles being exposed. So therefore, a powdered solid is going to react loads quicker than larger lumps. It goes down back to the same sort of logic of, though it's just dissolving, if you put a sugar cube or powdered sugar into your tea, one will dissolve quicker than the other. And the one that's going to dissolve quicker is going to be your individual granules of sugar, just because we've got that larger surface area. Therefore, when we're making catalysts to put in things like catalytic converters, we make these finely divided for that reason. We don't want this big lump of catalyst, because actually that's just going to slow everything down. We want it to be increasing as much as possible. So in many organic reactions, there are two liquid layers and one aqueous, and then the other non-aqueous. So what will happen is, if we shake the mixture, that can increase the rate as an emulsion is often formed. So basically, we've got our two liquid layers, we have an aqueous and a non-aqueous, and if we shake them about, we get an emulsion to form, and so then the area of the boundary layers is increased, giving more collisions. So basically, if we look at that block, it's got 30 square units surface area. Cut that block up into smaller pieces, we've got 54 square units. So we've got an increased surface area. It's the same as when we talk about in biology about increasing the rate of diffusion, increasing the rate of osmosis. We want a larger surface area. The more surface area, the more chances we have of those collisions to happen. Increasing temperature. This is another favourite in chemistry and biology. So if we increase the temperature, increasing the temperature increases our rate of reaction, because particles get more energy, therefore they can overcome the energy barrier, that activation energy. Energy barrier particle speeds also increase, so collisions are more frequent. So energy changes during a reaction. That's really important to remember. Okay, so as a reaction takes place, the enthalpy of the system rises to its maximum, its activation energy, and then it falls. A minimum amount of energy is required to overcome the activation energy. So regardless of if we're talking about an exothermic reaction or an endothermic reaction, our energy is always going to rise to a maximum and then fall. It just might not rise as much or fall as much depending which way we're going. So the minimum amount of energy is our activation energy, and only those reactants with energy equal to or greater than this value will react. If we give more energy to our reactants, then they're more likely to react. Therefore, if we increase the temperature of our reactants, they get more energy. If they've got more energy, they're more likely to overcome the energy barrier. Also, when they're faster, they also have more collisions. So we're sort of increasing two at the same time by increasing temperature. So according to kinetic theory, all particles have to have energy. So the greater their temperature, the more energy they possess. The greater their kinetic energy, the faster they travel. So we're sort of helping one to the other. So Zartman heated tin in an oven and then directed the gaseous atoms at a rotating disc with a slit in it. Any atoms that went through the slit hit the second disc and solidified on it. Zartman found that the deposit was spread out and was not the same thickness throughout. So what this proved that there was a spread of velocities and the distribution was uneven. And that's really, really important, that we're going to have different velocities and different distributions. And why is that going to happen? Well, actually, because we have an increase in energy and we have that decrease in energy. So experiments show that due to many collisions taking place between molecules, there is a spread of molecular energies and velocities. So no particles have zero energy or velocity. Some have very low and some have very high energy velocities. Most have intermediate. So this is the Maxwell-Boltzmann distribution of molecular energy. We have our molecular energy here and the amount of them. So most of them are in the middle. We have a few with really, really high energy, a few really, really low, but never zero. So we have this distribution of molecular energy. So not all of our particles are going to have the same amount of energy and velocity. And that's really, really important to remember. So just because we're heating up all these reactants to the same temperature, they're not all going to have the same energy and velocity. Some are going to have slightly more, some are going to have slightly less, and we'll get a big range in the middle that have similar. So increasing the temperature alters this distribution. So what this does is we get a shift to higher energies and velocities. So our curve gets broader and flatter due to the greater speeds of that spread of values. So our area under our curve stays constant because our number of particles aren't changing, but actually we're getting more with the higher energies because we're increasing them a little bit more. If we decrease the temperature, this also alters the distribution. They have less energy. So we will then find that we'll have more particles with less energy. So our curve becomes narrower and more pointed due to the small spread of values. But again, our area under the curve will stay constant because our number of particles remains the same. So this is all of them on there. So most important thing, no particles have zero energy or velocity. All particles have some form of energy. Some particles will have a very low energy, some have a very high energy and velocities, but most have intermediate. As the temperature increases, our curves flatten, broaden, and shift to higher energies. If we decrease our temperature, our curves narrow, have a higher point, and shift to lower energies. And then we have our activation energy. So the activation energy is the minimum energy required for a reaction to take place. And this is our number of molecules with sufficient energy to overcome the energy barrier. So most of them are in this intermediate area. So actually they do not have enough energy to overcome the activation energy. So the area under the curve below EA corresponds to our number of molecules with sufficient energy to overcome the energy barrier and react. So if we look at these together, if we increase our temperature, we've actually then increased our amount of particles that are then in this area for increasing the temperature. What I'm going to do is I'm going to stop there. I'm going to carry on with this tomorrow. So I'll pick up from the same place